Right now, in your pocket sits a device more powerful than a 1960s supercomputer, and every bit of it runs on a technology discovered almost by accident over 200 years ago. Before electricity could be stored, the world ran on fire, wind, and muscle. Every machine that moved needed a constant, burning source of power. Nothing could be portable. Nothing could be wireless. In 1936, a German archaeologist named Wilhelm Koenig was sorting through storage at the Baghdad Museum in Iraq when he noticed a small, unremarkable clay jar. The jar was roughly 14 centimeters tall, sealed with asphalt, and inside, a copper cylinder wrapped around an iron rod. No label, no explanation. Koenig dated the object to the Parthian era, roughly 200 years before Christ. He published a bold theory. It was, he claimed, an ancient electric battery. The chemistry is real. Fill that jar with an acidic liquid, grape juice or vinegar, and the copper and iron electrodes produce roughly 1 volt of electricity. No one agrees what it was actually used for. Some archaeologists suggest electroplating jewelry. Others say it was just a storage vessel. Without clear evidence of wires, the mystery stays unsolved. Jump nearly 2,000 years forward. In Bologna, Italy, a professor of anatomy named Luigi Galvani spends his days doing what anatomists do, dissecting frogs. One afternoon, Galvani's metal scalpel, carrying a small static charge from a nearby machine, accidentally touches the exposed sciatic nerve of a dead frog. The leg kicks. Galvani is transfixed. He calls the phenomenon animal electricity. His theory is that life stores electricity inside tissue and muscle, and death releases it. He spends years stringing frog legs from brass hooks on iron railings, watching them twitch in the wind during thunderstorms. His neighbors, understandably, have concerns. In 1791, Galvani publishes his findings in a landmark paper. It reaches scientists across Europe, including one man in Pavia who reads every word with deep skepticism. Alessandro Volta is a physicist, precise and methodical. He respects Galvani but disagrees fundamentally. The electricity, Volta believes, does not come from the frog. Volta's hypothesis: when two different metals touch, brass and iron, zinc and silver, they generate a small electric current. The frog's leg merely detects it. What follows is one of the great scientific rivalries of the century. Galvani publishes rebuttals. Volta counterargues. Letters grow sharper. Colleagues choose sides. It gets personal. Volta removes the frog entirely. He stacks discs of zinc and silver, separated by cardboard soaked in brine, one on top of the other. He connects the ends. A steady current flows. In 1800, Volta writes to the Royal Society in London announcing his invention. He calls it an artificial electric organ. History calls it the voltaic pile, the first true battery. Napoleon Bonaparte, who styled himself a patron of science, reads the announcement and summons Volta to Paris. After watching a demonstration, he awards him a medal and a substantial pension. Within months, scientists across Europe are building their own piles. Within a year, William Nicholson and Anthony Carlisle use one to split water into hydrogen and oxygen, the birth of electrochemistry. In 1807, British chemist Humphrey Davy builds the largest voltaic pile yet, over 2,000 cells stacked on a table, and uses it to isolate potassium and sodium for the first time. For 3 decades, the voltaic pile is the most powerful scientific instrument on Earth, funding breakthroughs in magnetism, chemistry, and the very nature of matter. But Volta's pile has a critical weakness. The cardboard rots, the solution degrades. After a few hours, the current fades and the pile must be rebuilt. Brilliant but fragile. In 1836, British chemist John Frederick Daniel solves the problem with a two-chamber design using a porous pot to separate two electrolytes. The current now holds steady for days. The timing could not be better. Electric telegraphs are spreading across continents, and they need reliable, sustained current over long periods. The Daniel cell powers them perfectly. By 1866, batteries help carry the first lasting transatlantic telegraph cable. For the first time, a message travels from London to New York in minutes. Also in 1866, French engineer Georges Leclanché develops a cell using zinc and manganese dioxide, cheaper, more portable, and far easier to manufacture at scale. By 1886, German scientist Karl Gassner seals Leclanché's chemistry into a zinc casing with no liquid inside. The dry cell is born, the ancestor of every AA battery ever made. Manufacturers begin producing them by the millions. By the turn of the century, you could walk into a hardware store and buy a battery for close to 1 penny. Thomas Edison spent years trying to build a better battery for electric cars, which did exist in 1900. His nickel-iron cell never caught on. The gasoline engine won. Through 2 world wars, the battery shrinks and specializes. Submarines depend on them. Soldiers carry radios powered by them. Bombers navigate by instruments they drive. Demand becomes industrial. In 1947, the transistor is invented at Bell Labs. Electronics begin to shrink. And as they shrink, demand for smaller, lighter, longer-lasting batteries grows into something enormous. Lithium is the lightest metal on the periodic table. It gives up electrons readily, which means high voltage in a small package. Scientists begin serious experimentation in the 1970s. Early lithium batteries had a dangerous habit. They caught fire. Unstable chemistry, fragile cell designs. Several major research programs stall. The industry hits a wall. Through the 1980s and 90s, 3 researchers, John Goodenough, M. Stanley Whittingham, and Akira Yoshino, each solve a different critical piece of the puzzle. In 2019, all 3 share the Nobel Prize in Chemistry. Goodenough receives it at age 97, the oldest Nobel laureate in history. In 1991, Sony releases the first commercial lithium-ion battery inside a camcorder. Within a decade, it is inside every laptop. Within 2 decades, every phone on Earth. Your phone battery is a thin pouch of layered lithium compounds. Cathode, anode, electrolyte, miniaturized beyond anything Volta could have imagined, yet running on the same electrochemical principle. Every time you plug in your phone, lithium ions migrate between electrodes through the electrolyte, storing energy chemically. Volta's salt-soaked cardboard, perfected over 2 centuries. Electric vehicles are now the fastest-growing segment of the global car market. The battery that defeated Edison has finally come of age, over 200 years after Volta's first pile. Utility companies are now building battery storage facilities the size of city blocks, banks of lithium cells storing solar and wind energy, releasing it when the sun sets and the wind stops. Researchers are racing towards solid-state batteries, no liquid, no fire risk, potentially twice the energy density. Others are developing sodium-ion cells that need no lithium at all. The next chapter is open. In a certain sense, Galvani was right. The nerve impulses firing in your brain and muscles are electrochemical, ionic currents crossing biological membranes. Animal electricity is real. He just found it in the wrong place. Volta and Galvani never reconciled. Galvani died in 1798, 2 years before the voltaic pile reached the world. He never knew his rival was correct, or that his twitching frog had made it all possible. And that clay jar in Baghdad, whether or not it was ever an intentional battery, it sits in the Iraq Museum today. a reminder that humanity may have been chasing stored electricity for far longer than we know. The battery is invisible in daily life, tucked inside every device, never seen, utterly taken for granted, until the moment it reaches 0%. Then, it is the only thing in the room. Every wireless earbud, electric toothbrush, pacemaker, Mars rover, and phone on Earth traces its silent power to a dead frog twitching on a dissecting table in Bologna in 1786. This is Origins. Subscribe and come back tomorrow. There's a new origin every single morning.